Hello, my name is Ron Wade, Principal System Engineer in the Timing Products Division of Renesas Electronics, and I'm back with another in our series on PCI reference clock jitter. In this part, we will be talking about PCI Express transport delay. So, transport delay applies to PCIe common clock architectures, and it is essentially trying to measuring the difference in delay between the data reaching the D input to the receiver latch and the clock edge reaching the clock on the latch that clocks it in. And to do that, we start with the reference clock and we trace its path through the transmitter this way and compare it to the length of the path of the reference clock through the receiver, which is this way. Now, this is consisting of several different pieces. There's the L1 length, which is from the ref clock routed to the transmitter. There is an insertion delay of 1 nanosecond, up to 1 nanosecond maximum, assigned to the transmitter chip itself. There's the length of routing physically outside the transmitter on this PCB to get to the receiver. There's the insertion delay at the receiver chip. And then going from on the other side, we take the ref clock and we follow its PCB route to the receiver chip itself and then through the device to the receiver latch. Now, I'm using a single value of ID1 and ID2 because the spec is basically giving us the difference between the data and clock internally to the chip. So we only need one value, knowing that it's worst case of 1 nanosecond for each chip. So we can measure the transport delay in length or in units of time. If we measure in length, we will need to convert it into time by using the intrinsic propagation delay of the FR4, for instance, the PCB material, to do that conversion. So the routing difference between the top here and the bottom is what's referred to as transport delay. So let's have some examples now. So again, it's defined in units of time, and what we do is we sum up the top delay, and then we subtract the bottom delay and take the absolute value. This could be a positive or a negative number, but we're only interested in the magnitude. So for this case, let's set the values. L1 is 2 nanoseconds. The insertion delay for SOC1 is 1 nanosecond. We have 10 nanoseconds of trace delay on the PCB in the data channel. We have another insertion delay of 1 nanosecond at the receiver chip. And then L3, which is from the ref clock to the RX latch in the receiver chip, is 5 nanoseconds. So to find out what the transport delay value is here, in other words, the delta between the data and the clock, we sum up the top and subtract the bottom, and we get 14 minus 5, which is 9 nanoseconds. PCI Express has a default value of 12 nanoseconds, which we'll delve into in the next module where we actually create the PCIe jitter module. So now let's take this same drawing and we'll assign units of length to the various parameters. And in this case, we've got a couple of things we can do. If we know the routing inside the SoC, we can assign a length to it. However, we probably know that it's 1 nanosecond, so you could just put the time value here and add it at the end. Usually what happens is we just have one value that is encompasses everything, but to know where it came from is important. So in this case, we're going to set L1 to be 5 centimeters, and then we have the internal delay is, we're calling it 2.5 centimeters because we know the trace length inside the package. We're going to go with a 12.5 centimeter length on the data channel. We have another 2.5 centimeters here, and then this length is 25 centimeters, let's say, from the reference clock all the way to the receiver latch. So if we do the addition, we add up the top and we get 22.5 centimeters, and we subtract the bottom, which is 25 centimeters, which gives us, say, an absolute value of 2.5 centimeters. And I'm saying that our propagation delay in the part or on the circuit board is 62 picoseconds per centimeter. So when we multiply the propagation delay, the intrinsic propagation delay times the length, we get a transport delay of 0.155 nanoseconds or 155 picoseconds. Again, much less than the 12 nanosecond spec, and so it's all okay. If you have a situation where you've done your math on this on your system and you have a transport delay that's bigger than 12 nanoseconds, you just plug it into the equation and solve your value. And as long as you're underneath the limit for PCIe jitter, you're going to be fine. But you need to change from the default of 12 and plug it in. Just a piece of history. Originally, PCIe had a transport delay default of 10 nanoseconds. And then how it got to 12 is they left the 10 nanoseconds of routing, but they just added in the insertion delay of the transmitter chip and the receiver chip, limiting them to 1 nanosecond each. So you had 10 plus 1 is 12, which is the current specification, which includes the insertion delays. Okay, so PCIe transport delay does not apply to IR architectures. And the reason is because there is no phase relationship between ref clock 1 and ref clock 2. I could still do this addition if I wanted to for the transmit path, but there's no commonality between these two reference clocks, which means that I can't generate any kind of equation that relates the clock at the receiver latch to the data at the receiver latch from a transport delay viewpoint. So there's no way to generate the equation, and from the transport model, the jitter transfer model that is derived for IR architectures, there's no need for it. So just keep in mind, transport delay is a function of common clocked architectures and does not apply to IR clocked architectures. Okay, that covers transport delay. And the next module in the series will begin to build out the PCIe reference clock jitter model, and we'll get to see what the impact of different transport delays has on the jitter transfer function. So I thank you for watching and take care.